Stegosaurus, the most misunderstood dinosaur in history. Another planet. Picture an Earth with no flowers. Not a single one. No daisies, no roses, no dandelions. No wheat fields, no grass, no fruit trees. Where meadows should be, endless fern savannas. Where forests should stand, dark araucaria groves, towering like enormous pines with thick, scaly bark. Horsetails growing to head height line every riverbank. The ground smells of wet soil and spores. Now remove the Rocky Mountains. Erase the Alps. The Himalayas don't exist. The world map you know, gone. In its place, two vast landmasses divided by warm, shallow seas. Laurasia to the north, Gondwana to the south. Between them, the Tethys Ocean, warm as a bath. CO2 in the atmosphere sits at around 1,200 parts per million, more than 3 times higher than before the Industrial Revolution, more than double what we breathe today. No ice caps. Temperatures run 5 to 10 degrees hotter than now. This isn't the tropical jungle you've seen in movies. It's something stranger, a semi-arid greenhouse planet, where conifer forests push to the poles and the tropics are vast, seasonally scorched wastelands. This is the late Jurassic, 155 to 145 million years ago. 10 million years, a stretch more than 3 times longer than the entire existence of the human genus. And it's here, in this utterly alien world, that one of the most recognizable silhouettes in the history of life appeared. A hunched back, 2 rows of plates jutting toward the sky, 4 spikes at the tip of a heavy tail, a tiny head hanging close to the ground. Stegosaurus. Any 5-year-old can pick it out of a lineup. It's in every children's book, every toy store, every museum gift shop. Second most recognizable dinosaur after T-Rex. And yet, arguably the most misunderstood animal that ever walked this planet. Because almost everything science once said about Stegosaurus turned out to be wrong. Its name, a mistake. Its posture, a mistake. The arrangement of its plates, a mistake. The famous second brain, a mistake. And even today, 150 years after its discovery, paleontologists still can't agree on what those backplates were actually for. This isn't just a story about a dinosaur. It's a story about how hard it is to learn the truth about a creature that died 150 million years ago. About how science argues with itself, corrects itself, and slowly, inch by inch, moves closer to something resembling the truth. But before we start pulling away the masks, and we will, one by one, we need to understand the world Stegosaurus actually lived in. Because without context, it's just a picture. With it, it comes alive. The main stage, the Morrison Formation, a vast layer of sedimentary rock across the American West, Colorado, Utah, Wyoming, Montana, New Mexico. Age, 156 to 146 million years old. Floodplains, river channels, seasonal lakes. The climate, semi-arid, seasonally wet. Not the lush tropical jungle of Jurassic Park. Something closer to the African savanna, with gallery forests crowding the riverbanks. And what a savanna it was! At the top of the food chain, Allosaurus, accounting for roughly 3/4 of all large predators in the formation. 9 meters long, over a ton, with jaws that opened like scissors. Alongside it, Ceratosaurus, with a horn on its snout, and the enormous Torvosaurus, stretching up to 10 meters. Among the plant eaters, Diplodocus, whose tail cracked like a whip. Brachiosaurus, looking out at the world from 4 stories up. Camarasaurus, the most common sauropod in the entire formation. Stegosaurus occupied the middle of this ecosystem. Its head hung no higher than a meter above the ground, far below any large sauropod. While Brachiosaurus stretched toward the treetops and Diplodocus browsed at mid-height, Stegosaurus worked the ground floor. Ferns, horsetails, cycads, ginkgos, low-growing conifers. It cropped them with a horny beak and processed this tough vegetation in ways scientists still don't fully understand. Its teeth were too weak for grinding, and gastroliths, the swallowed stones some dinosaurs used like a built-in food processor, have never been found near its skeletons. Each animal ate at its own level. Direct competition was minimal. The system worked. Now, a number that should stop you cold. Stegosaurus went extinct at the Jurassic-Cretaceous boundary, around 145 million years ago. Not a single Stegosaurus species is known from Cretaceous rocks. And T-Rex didn't appear until 68 million years ago. The gap between Stegosaurus and T-Rex, roughly 80 to 84 million years. The gap between T-Rex and us, only 66 million years. We are chronologically closer to Tyrannosaurus rex than T-Rex was to Stegosaurus. If T-Rex could have looked back in time as far as we look back at it, it would have seen Stegosaurus already long extinct and buried in stone. When those two animals stand side by side in Jurassic Park, that's a meeting of creatures separated by a gap larger than the gap between T-Rex and you. They never shared the same world, not once. Remember that number, 80 million years. It'll come up again. Now, let's talk about how we actually discovered this animal. Because it wasn't a triumph of careful science. It was something closer to a disaster, complete with spies, dynamite, and a chain of errors that took a century to untangle. Mistake after mistake. March 20th, 1877. The western slope of a rocky ridge north of Morrison, Colorado. Arthur Lakes, a geology teacher and talented draftsman, 32 years old, is scrambling over exposed rock with his friend Henry Beckwith, a retired naval officer. They're looking for fossilized leaves. Instead, they find enormous bones. Tail vertebrae. A strange, flat, bony plate. Several postcranial fragments. Lakes sketches everything in meticulous detail and mails it all to Professor Othniel Charles Marsh at Yale University. Marsh examines the package and makes the first mistake. He concludes he's looking at a giant aquatic creature, something vaguely turtle-like. That's why he names it Stegosaurus, roof lizard, from the Greek stegos, roof, and sauros, lizard. In his hypothesis, the bony plates lay flat across the back, overlapping like tiles on a rooftop. Stegosaurus was not a turtle. The plates did not lie flat, but the name stuck. the first mistake became immortal. The official description appeared in December 1877 in the American Journal of Science, in the same article where Marsh described Allosaurus and Apatosaurus, three icons of paleontology announced in a single journal issue. But to understand why Marsh was in such a rush to publish, you need to know about one man, Edward Drinker Cope. Marsh and Cope had once been friends, both brilliant paleontologists, both with egos the size of continents. Their friendship collapsed around 1870 after a series of mutual grievances. The final break came when Cope mounted the head of a long-necked marine reptile called Elasmosaurus on the wrong end, on the tip of its tail. The error was pointed out publicly by their mutual colleague Joseph Leidy at a meeting of the Academy of Natural Sciences in Philadelphia in March 1870. Marsh made sure everyone knew about it. Cope tried to buy up the entire print run of the journal to bury the evidence. It didn't work. Both men remembered. From that moment, war was declared. The Bone Wars, roughly 1877 to 1892, are one of the most extraordinary chapters in the history of any science. Before the conflict began, only 9 dinosaur species had been formally described in North America. 9. By the time it ended, Cope had named 56 new species, and Marsh had named 80. With other participants, more than 140 in total. With other Stegosaurus, Triceratops, Allosaurus, Diplodocus, all trophies of Marsh. The methods were anything but scientific. When Marsh's team finished at a quarry, he gave explicit orders: blow it up with dynamite. Better to destroy a paleontological treasure than let it fall into Cope's hands. Cope's men did the same. At the Como Bluff Quarry in Wyoming, the two teams literally threw rocks at each other. William Carlin, working for Cope, once locked William Reed, working for Marsh, inside a railway station to stop him loading crates of bones onto the departing train. Marsh ran a network of informants and assigned Cope a code name, simply the letter B. Dynamite, spies, rocks thrown at heads, code names. This is not a screenplay. This is American paleontology in the 1870s. The finale was catastrophic for both. Marsh burned through his inheritance from his wealthy uncle George Peabody, the man who funded Yale's Peabody Museum, combined with his government salary, and ended up penniless. Cope was forced to sell his entire fossil collection and downsize his home. Both died broke. Cope in 1897, Marsh in 1899. There's a story, imperfectly documented, possibly apocryphal, that Cope arranged for his brain to be weighed after death and compared with Marsh's as a final scientific argument. Marsh declined. Whether or not it happened, it fits both of them perfectly. In the middle of all this, Stegosaurus became one of the great trophies of the race, and one of its greatest victims, because Marsh's haste introduced errors that paleontology spent more than a century correcting. The trail of mistakes is worth tracing. In 1877, Marsh depicted the plates lying flat, like roof tiles. Mistake 1. By 1891, he'd drawn a single row of vertical plates down the spine. Mistake 2. In 1901, paleontologist Frederick Lucas concluded the plates were arranged in matching pairs, 2 symmetrical rows. Mistake 3. In 1910, Richard Swan Lull built the first mounted Stegosaurus skeleton at the Peabody Museum, again with paired plates. Mistake 4. As early as 1914, a paleontologist named Charles Gilmore proposed an alternating, staggered arrangement, but nobody listened. In 1987, Stephen Zirkus argued for a single row. Only in 1998 did Kenneth Carpenter, after examining several complete articulated specimens, skeletons preserved with bones still in their original positions, confirm what Gilmore had proposed 84 years earlier. The plates stand in two alternating, offset rows. No two plates from the same animal are identical in shape or size. A staggered zigzag, not a mirror image. 120 years, 4 competing versions. That's how long it took to correctly place the plates on the back of a single dinosaur. In his race to publish, Marsh described more than 10 stegosaur finds as separate species. Most turned out to be duplicates, misidentifications, or fragments too incomplete to diagnose. Today, only 3 valid species are recognized. Stegosaurus stenops, the most familiar and best studied, the species Sophie belongs to. Stegosaurus ungulatus, larger with longer spikes. And Stegosaurus sulcatus, known only from fragments. The original species, Stegosaurus armatus, the one Marsh described in 1877, was eventually declared a nomen dubium, a doubtful name. The type specimen is too fragmentary for a reliable diagnosis. In 2013, the International Commission on Zoological Nomenclature officially designated Stegosaurus stenops as the type species of the genus. The first described Stegosaurus lost its status as the real one. A name born from a mistake. Marsh thought the plates looked like a roof. Outlived Marsh. Outlived all his misconceptions. And outlived every correction that followed. Roof lizard is still roof lizard. There was never any roof. But not all of Marsh's errors were about the plates. In the 1880s, he made perhaps his most famous mistake of all. Examining the sacral region of the spine, he found a cavity in the hip vertebrae roughly 20 times larger than the cranial cavity of the brain. The conclusion seemed irresistible. Stegosaurus had 2 brains, one in the head, one in the hips. Marsh himself walked back the idea before long, but the myth had already escaped. Stegosaurus had 2 brains, one in its head and one in its butt, remains one of the most durable misconceptions in popular science. You can still find it in school corridors, museum gift shops, and, if you're unlucky, on actual biology tests. The truth is less exciting. There was no second brain. That enlarged cavity is a feature of the spinal cord canal, seen in both stegosaurs and sauropods. Its most likely function, housing a glycogen body, a structure analogous to one found in the same region in modern birds, probably supplying the nervous system with glycogen as a fast energy source. There was also a major lumbosacral nerve plexus here, coordinating the hind limbs and tail. Not a brain, but something closer to a local command center, capable of triggering reflex responses before any signal could complete the round trip to the actual brain. Not a second brain, but functionally, genuinely interesting. And while we're clearing up mythology, the brain the size of a walnut is also wrong. The actual brain was shaped more like a bent sausage, about 3 centimeters long, weighing 70 to 80 grams. For a body weighing several tons, that ratio is extraordinarily small. Stegosaurus had an encephalization quotient of around 0.2, one of the lowest on record for any dinosaur. Carnivorous theropods score between 1 and 2. A modern crocodile scores 0.1 to 0.3. Stegosaurus was in crocodile territory. But here's the thing. The next time someone uses dumb as a Stegosaurus as an insult, consider this. No species in the genus Homo has survived for even 1 million years. Stegosaurus lasted 10 million. Through climate swings, droughts, floods, and continuous predator pressure. With a sausage-shaped brain. Maybe we're measuring intelligence by the wrong standard. By the early 20th century, science had gotten almost everything about Stegosaurus wrong. Its posture, its plates, its neurology, its way of life. It would take an entirely new century and one specific skeleton to start seeing this animal as it actually was. The masks come off. In 2003, a professional fossil hunter named Bob Simon was surveying the Red Canyon Ranch in Wyoming. What he found there changed Stegosaurus paleontology permanently. A skeleton, nearly complete. More than 360 bones, 85% intact. 5.8 meters from nose to tail. And, most importantly, the bones were preserved in 3 dimensions. No crushing, no distortion, still carrying their original volume and geometry. The Natural History Museum in London acquired the skeleton and named it Sophie, after the daughter of the primary financial donor. In December 2014, Sophie went on public display. The most complete Stegosaurus skeleton in the world. And the discoveries started immediately. In March 2015, a team from Imperial College London, led by Charlotte Brassey and Susanna Maidment, built a complete 3D digital model of the skeleton. For the first time in the history of Stegosaurus research, it was possible to estimate the animal's mass through computational modeling rather than guesswork. The result? Approximately 1,600 kilograms, roughly the size of a small rhinoceros. There's a catch. Sophie died as a young adult. She hadn't reached full size. Mature stegosaurs were considerably heavier. How much heavier? Stegosaurus stenops reached 6.5 meters and weighed up to 3.5 tons. The largest species, Stegosaurus ungulatus, stretched up to 7 meters and weighed nearly 4 tons. Exceptional individuals may have hit 7.5 meters and over 5 tons. Total height, plates included, roughly 3.3 to 4.5 meters, taller than a city bus. For comparison, a white rhinoceros weighs about 2.3 tons. The average Stegosaurus outweighed 1.5 rhinos. The largest were comparable to a small elephant. Here's the first mask Sophie helped remove. It had long been assumed that Stegosaurus was a dim-witted herbivore capable of eating only the softest ferns. Small head, tiny teeth, what would you expect? But in 2016, an international team from Bristol, Birmingham, Manchester, and London ran biomechanical modeling on Sophie's jaws and got a surprise. The bite force of Stegosaurus was comparable to that of a cow or sheep. Not powerful by predator standards, but more than enough for tough cycad leaves and conifer needles, not just soft-ground ferns. Stegosaurus wasn't a picky eater. It was an indiscriminate grazer, capable of handling most of the plants in its environment. The skull itself, though, remains astonishing. Total length, just 40 centimeters, on a body up to 7.5 meters long. The head was less than 5 to 6% of the animal's total length, one of the smallest proportions among large dinosaurs. About 78 teeth, small, triangular, leaf-shaped. The jaws moved only vertically. Stegosaurus couldn't chew in any familiar sense, only shear and swallow. The second mask, posture. Stegosaurus's front legs were significantly shorter than its hind legs. That's what creates the distinctive hunched silhouette. Marsh in the 1880s actually thought it might be bipedal. He was wrong. The animal was far too massive for that. But here's where it gets interesting. Paleontologist Robert Bacher proposed that Stegosaurus could rear up on its hind legs, bracing against its tail like a tripod, to reach vegetation at heights inaccessible from a normal stance. In that position, it would have reached roughly 6 meters, up to the second floor of a building. The skeletal mechanics allow it. Powerful hind limbs and a thick, robust tail could theoretically support the body's weight. The hypothesis remains contested. No tracks, no preserved posture impressions, no full biomechanical muscle reconstruction models to confirm it. Most researchers treat Stegosaurus as a strict quadruped. But the fact that how many legs did Stegosaurus walk on is still a live scientific question tells you something about how much we still don't know. Maximum walking speed, around 15 to 18 kilometers per hour. Any faster, and the hind legs would have started overtaking the front ones. Not the fastest animal in its ecosystem. Allosaurus could certainly outrun it. But Stegosaurus had a trick. Bacher also established that to defend against attack from the rear, Stegosaurus could pivot sharply on its hind legs, using its shorter front legs as a brace. For a creature weighing several tons, this was a surprisingly quick maneuver. An armored spinning top with 4 bone spikes on its tail. Slow in a straight line, dangerous up close. The third mask, and the most important, involves its supposed stupidity. Yes, the brain was tiny. Yes, the encephalization quotient was among the lowest on record. But that brain didn't stop Stegosaurus from being one of the most durable animals in the history of complex vertebrate life. 10 million years. The glycogen body in the hip region and the lumbosacral nerve plexus provided reflexes that could fire before any conscious response was possible. The tail was already moving before the brain had finished processing the threat. Not intelligence as we understand it. Something that worked just as well. Sophie stripped away these masks. Stegosaurus turned out to be neither helpless nor simple. But one mask remained, the biggest, the most stubborn, the one that has resisted every attempt to pull it off for 150 years. The plates. The Great Debate. 17 to 22 bony plates, standing in 2 alternating rows along the spine. The largest ones, above the hips, reach 60 centimeters tall and 60 centimeters wide, about the footprint of a small coffee table standing on edge. These are modified osteoderms, the same type of structure as the scales embedded in a crocodile's skin, scaled up to almost absurd proportions. What were they for? Paleontologists have been asking that question for 150 years. And for 150 years, they cannot agree. Let's go through each hypothesis, because in this debate, you can see both the beauty and the genuine frustration of the scientific method. Hypothesis 1. Radiator. In 1976, paleontologist James Farlow and colleagues published a paper in Science proposing that the plates functioned as forced convection radiators, essentially cooling fins. Like the fins on an engine, only made of bone. With air moving past them, the plates could shed body heat far more efficiently than bare skin. The key evidence? A branching network of blood vessel channels running through the interior of each plate. In 2010, Farlow, working with Hayashi and Tattersall, CT scanned the plates and compared their internal architecture to alligator osteoderms. The results were striking. At the base of each plate, large openings led into a central channel, from which branching vessels spread upward through the bone. An entire vascular distribution system embedded in the structure. Computer simulations suggested that by regulating blood flow, Stegosaurus could theoretically vary the heat output of its plates by up to 30%. An elegant hypothesis. But it has a problem. The problem is keratin. A study of a well-preserved Hesperosaurus, a close relative, that retained soft tissue impressions revealed that the plates were sheathed in keratin during life. The same material as claws, horns, and beaks. Fine parallel grooves ran across the surfaces, consistent with a keratinous covering. That sheath reinforced the plates and gave them sharp edges. It also acts as a thermal insulator. Wrapping a radiator in insulation defeats the purpose. This doesn't kill the thermoregulation hypothesis entirely. Keratin is imperfect insulation, and some heat exchange would still occur. But it's a serious objection the hypothesis has never fully answered. Hypothesis 2. Armor. At first glance, obvious. What else would bony plates be for? As far back as 1961, however, paleontologist Davitashvili pointed out the problems. The plates are too fragile and too poorly positioned for effective protection. They run along the spine, leaving the sides, belly, and limbs completely exposed. CT data confirms this. The interior is spongy, cavity-filled bone with thin walls, not solid armor. And the plates are saturated with blood vessels. Any significant damage would cause heavy bleeding. The tail spikes, by contrast, are made of dense, compact bone, clearly a weapon. The plates were something else. Hypothesis 3. Species Recognition Badge. In 2005, researchers proposed that the plate's primary function might have been species identification. The plates differ so dramatically between stegosaurid species that they could have helped animals recognize their own kind. Logical. But critics noted the obvious problem. Natural selection rarely maintains metabolically expensive structures, requiring large investments of calcium and energy over a lifetime, purely as a name tag. Deer antlers also help distinguish species, but that's not why they evolved. Hypothesis 4. The peacock's tail. And here's where it gets most interesting. In 2015, researcher Evan Saida from Princeton was working at a site in Montana where many individuals of a single stegosaur species were found in one stratigraphic layer. He showed that in Stegosaurus mjosi, the plates come in two distinct forms: broad, oval ones with a surface area roughly 45% larger, and tall, narrow ones. No intermediate shapes. The difference wasn't explained by age. and the animals clearly belonged to the same species. Real sexual dimorphism. Wide plates, presumably the male's display structures. Narrow, the female's. The equivalent of a peacock's tail, a lion's mane, a set of elk antlers. In April 2025, a preprint on bioRxiv confirmed sexual dimorphism in Hesperosaurus using independent statistical methods. It hasn't yet completed peer review. Treat it as promising but provisional. But here's a discovery that may be more satisfying than any single hypothesis. The plates appear to have changed function with age. A 2012 study by Hayashi, examining 8 individuals across a range of ages, found that in younger adults, the plates have an extensive vascular network, consistent with display or thermoregulation. In those same younger animals, the tail spikes still have spongy, relatively soft bone. But in older adults, the pattern reverses. The spikes develop dense, compact bone, genuine combat weapons, while the plates become less vascularized. The biological strategy shifted as the animal matured. Young Stegosaurus displayed. Old Stegosaurus fought. There's more. A 1986 study by de Bouffrenil, Farlow, and de Riclet found what you might call a growth paradox. In medium-sized Stegosaurus, the body skeleton was already showing signs of slowed growth. But the plates were still growing rapidly, with no growth arrest lines and a dense vascular network. The plates were in a hurry. Like a young deer growing its first set of antlers, needed urgently before the first breeding season. And one detail that genuinely takes the breath away. In very young juveniles, the plates were tiny relative to body size, disproportionately small. If plates were critical for thermoregulation, juveniles would have needed them at least as much as adults. A smaller body has a higher surface area to mass ratio and is actually more vulnerable to overheating. But the juvenile plates were undersized. That's a strong argument for display, a tool that isn't needed yet because reproduction is still years away. And finally, the most beautiful idea and the least provable. Stegosaurus may have been able to blush at will. By pumping blood into the plates, it could flush them bright red, as a warning to a predator or a signal to a mate. At rest, they'd pale back down. The idea was first put forward by Kenneth Carpenter. No direct paleontological proof, skin color doesn't survive in the fossil record. But the biological mechanism is supported by anatomy. In living lizards, controlled blood flow to skin structures is well documented. Picture a Stegosaurus turning broadside to an approaching predator. Blood floods the plates. They flush deep red. The keratin sheath catches the light. The animal looks larger, more vivid, more dangerous. A living alarm signal. The traffic light of the Jurassic. Beautiful? Absolutely. Proven? No. But anatomically, entirely possible. Where does that leave us? Most researchers today agree on this much. The plates served multiple functions simultaneously, with the balance shifting depending on the animal's age and situation. Display, the dominant function. Thermoregulation, secondary, plausible but not essential. Protection, minimal at best. The most iconic feature of Stegosaurus still has no settled explanation. 150 years of research, 4 serious hypotheses, no final answer. That is science. Not a library of ready-made truths, an endless, honest approach toward them. But if the plates remain a mystery, there is one part of Stegosaurus about which we have zero doubt: its tail. The Thagomizer. Before we talk about the weapon, let me tell you about its name, because this story is one of the best things to happen at the intersection of science and popular culture in the 20th century. On May 27, 1982, the newspaper comic strip The Far Side, drawn by Gary Larson, published a single-panel cartoon. A caveman, acting as a university lecturer, stands at a blackboard showing a Stegosaurus. He points to the tail spikes and tells the audience, "Now this end is called the Thagomizer, after the late Thag Simmons." Pure invention. There was no Thag Simmons. But here's the remarkable thing. Before that cartoon appeared, Stegosaurus's tail spikes had no scientific name. None. Paleontologists used phrases like caudal spikes or tail osteoderms, but there was no agreed term. In 1993, paleontologist Kenneth Carpenter of the Denver Museum of Nature and Science was presenting at the annual meeting of the Society of Vertebrate Paleontology. Describing a specimen, he used the word Thagomizer. The room laughed. The term stuck. Then it spread. Today, Thagomizer appears in Smithsonian Institution publications, in the interpretive materials at Dinosaur National Monument, in BBC's Planet Dinosaur, and in The Complete Dinosaur, a major scientific reference. One of the very rare cases in the history of science where a newspaper cartoon became an official anatomical term. Larson was delighted. When biologist Dale Clayton named a newly discovered species of louse, an owl parasite, in his honor, Larson responded, "I considered this the highest honor. I understood that nobody was going to name a new species of swan after me. You have to grab these opportunities when they come." Among working scientists, Gary Larson is the most beloved cartoonist on the planet. His strips hang in hundreds of laboratories worldwide. Now, the weapon itself. 4 bony spikes, arranged in 2 pairs and angled roughly 45 degrees from vertical. Each spike, 60 to 90 centimeters long, about the span of an adult human forearm. The tail itself, on a total body length of 6.5 meters, comprised about a third of that, roughly 2.5 to 3 meters, supported by approximately 46 vertebrae. Here's the detail that made this tail genuinely lethal. Unlike most ornithischian dinosaurs, Stegosaurus had no ossified tendons running through its tail, first noted by Robert Bacher. This meant the tail was fundamentally more flexible than those of hadrosaurs or iguanodonts. A modified arrangement of intervertebral ligaments functioned like a spring, snapping the tail back into position after a strike, allowing for a rapid series of blows rather than a single swing. Not one shot, a combination, like a boxer working the body. In 2005, Kenneth Carpenter, the same person who introduced Thagomizer into scientific literature, together with Frank Sanders, Laurie McWhinney, and Lowell Wood, published a detailed mechanical analysis. At a tail tip velocity of 12 meters per second, over 40 kilometers per hour, with a tip mass of roughly 14 kilograms, a single spike delivered a force of 360 to 510 newtons. Given the small contact area of a spike tip, that translated to a local pressure of 13 to 18 megapascals. More than enough for a deep, penetrating wound. And now, the physical evidence. A piece of evidence from a Jurassic crime scene, preserved for 150 million years. In the collection of the Natural History Museum of Utah is a vertebra from an Allosaurus, recovered from the Cleveland Lloyd dinosaur quarry. That vertebra has a partially healed hole punched through one of its lateral processes. Carpenter and co-authors showed that the diameter, shape, and angle of penetration match a Stegosaurus tail spike precisely. Signs of bone remodeling around the wound's edges mean the Allosaurus survived the strike and lived long enough for healing to begin, but the cavity never fully closed, suggesting a fragment of spike had broken off inside the wound and remained there. An Allosaurus took a Stegosaurus spike through its vertebra. The spike may have broken off and stayed embedded. The predator survived and walked with that injury until it died. This is not a hypothesis. This is a piece of bone with a hole in it, 150 million years old. The evidence is unambiguous. But stegosaurs took damage too. In 2001, Lori McWhinney, Bruce Rothschild, and Kenneth Carpenter examined damaged tail spikes from Stegosaurus specimens at Como Bluff. Of 51 spikes examined, roughly 10% had broken tips with clear signs of healing. The spikes had snapped in combat, but the animal survived and lived on with healed stumps. Chronic osteomyelitis, bone inflammation consistent with infection, was recorded in several specimens. Stegosaurs fought, seriously, repeatedly, and survived, which from an evolutionary perspective means the weapon paid off. In 2011, German paleontologist Heinrich Mallison went further. He built a computer dynamic model of the tail of Kentrosaurus, an East African relative of Stegosaurus, and calculated tip velocity. The result? Over 40 meters per second, 144 kilometers per hour. Mallison concluded the tail was physically capable of breaking the ribs and facial bones of large predators. For context, Stegosaurus's Thagomizer was a penetrating weapon, a spike strike, a deep wound. The ankylosaur tail club was blunt force. Large ankylosaurs generated impact forces of up to 10,000 newtons, enough to fracture the ankle joint of a Tyrannosaurus. The tail of Diplodocus and its relatives functioned more like a whip, reaching tip velocities of around 30 meters per second. Spikes, clubs, whips. Three completely independent evolutionary answers to the same problem: how not to get eaten. There was a fourth answer, discovered only recently. And to tell that story, we first need to talk about Stegosaurus's extended family. The Dynasty. Stegosaurus was not an isolated species. It was part of a large, globally distributed family that spread across the entire planet, from Morocco to Chile, from Tanzania to China. Each member had its own solution to the problem of being a large, slow, plant-eating dinosaur in a world full of fast predators. Thyreophorans, shield-bearers, form one of the major branches of the ornithischian dinosaurs. The group includes stegosaurs, ankylosaurs, and their earlier common ancestors. They split from other ornithischians near the very beginning of the Jurassic, roughly 200 million years ago. By the middle of the Jurassic, they divided into two lineages, Stegosauria and Ankylosauria. And here's something that tends to surprise people. The earliest Thyreophoran looked nothing like either a stegosaur or an ankylosaur. It looked like a lizard wearing chainmail. Scutellosaurus lived around 196 million years ago in what is now Arizona. Body length, 1.2 meters, roughly the size of a large cat. And it moved on 2 legs. The only confirmed bipedal armored dinosaur. Hundreds of tiny bony studs ran down its back, embedded in the skin. A nimble 2-legged animal in a coat of bony armor. Hold that image, and then picture Stegosaurus. Same family. Nearly 200 million years of evolution separate a cat-sized sprinter from a 5-ton animal with plates the size of coffee tables on its back. Which of Stegosaurus's relatives is most remarkable? The competition is genuinely fierce. Here are 4 that each deserve their own video. Kentrosaurus, spiked lizard from the Tendaguru Formation in what is now Tanzania, one of the richest fossil sites in Africa. 4 to 4.5 meters long, described in 1915 by German paleontologist Edwin Hennig. Unlike Stegosaurus, Kentrosaurus had only small plates on its neck and forward back. The entire rear half was studded with spikes, including a distinctive pair angled outward from the shoulders. A walking hedgehog of the Jurassic. Its tail was the one Mallison clocked at 144 kilometers per hour. Smaller than Stegosaurus, arguably more dangerous per kilogram. Miragaia, the giraffe of the Stegosaurs. From Portugal, about 150 million years ago. The longest-necked stegosaur known, no fewer than 17 cervical vertebrae. Most stegosaurs have 9 or 10. Diplodocus, the long-necked sauropod, had 15. Miragaia had more than many sauropods. That neck was achieved through cervicalization. Front dorsal vertebrae gradually restructured and became neck vertebrae. Convergent evolution with the sauropod body plan, arrived at independently. When every other herbivore is grazing at ground level, the one that feeds a meter higher has access to food nobody else can reach. Adrodiclet, mountain lizard in the Berber language, the earliest reliably identified stegosaur in the world. 168 million years ago, in the Middle Atlas Mountains of Morocco. Described in 2019 by Susanna Maidment of the Natural History Museum in London, from a small collection of vertebrae and a humerus, sufficient for confident identification. The first stegosaur from North Africa. Its age pushed back the confirmed timeline of global stegosaur distribution significantly earlier than previously assumed. Adrodiclet, 168 million years ago. The last well-documented stegosaurs appear around 125 to 130 million years ago. And in 2024, Yanbeilong ultimus was formally described, a Cretaceous stegosaur from China, living between 113 and 100 million years ago, the latest known member of the entire group. Total duration of the Stegosaur dynasty, a confirmed minimum of 55 to 68 million years. The fourth relative is the most astonishing. In December 2021, the journal Nature published a description of Stegouros, a creature roughly 1.8 to 2 meters long, found in February 2018 in Patagonia, near the Valle de las Chinas. Age, approximately 74 million years. late Cretaceous. The name, covered tail, hints at what made it extraordinary: its tail. Nothing like it had ever been seen in paleontology. 7 pairs of lateral osteoderms forming a flat, fan-shaped structure. The closest analogy researchers reached for? The macuahuitl, the Aztec war club, a flat wooden weapon with obsidian blades set along its edges, only made entirely of bone, on a dinosaur's tail. Not spikes, not a club. A third type of tail weapon, a completely independent evolutionary solution that nobody had predicted. And what makes it stranger still, despite its stegosaur-like features, Stegouros is phylogenetically closer to the ankylosaurs. Together with Kunbatasaurus from Australia and Antarctopelta from Antarctica, it forms a distinct Gondwanan clade, Parankylosauria. The armored dinosaurs of the southern hemisphere went their own path and invented a weapon their northern relatives never arrived at. Spikes, clubs, bone Aztec swords. 3 independent inventions. Evolution wasn't copying. It was running parallel experiments. What happened to the stegosaurs in the end? They disappeared, quietly, without catastrophe. The last confirmed remains date to the early Cretaceous, tens of millions of years before the asteroid that ended the non-avian dinosaurs. 3 hypotheses, none with decisive support. The first is floristic. The decline of stegosaurs coincides with the decline of cycadophytes, displaced by angiosperms, flowering plants, a completely new type of vegetation that stegosaurs were not equipped to process. The flowers changed the world, and stegosaurs couldn't change with them. The second is competitive. Ankylosaurs and other armored dinosaurs expanded into the same ecological niches. More compact, lower to the ground, better armored. They may have displaced stegosaurs from the habitats they depended on. The third is geographic. Stegosaurs were a highly specialized group with a fragmented range, and as the continents drifted apart, isolated populations simply dwindled and vanished one by one. Direct evidence for any scenario remains thin. Stegosaurs simply disappeared. Gradually, without drama, without a single identifiable cause. A dynasty lasting more than 50 million years dissolved, quietly, into geological time. But to disappear from the Earth is not to be forgotten. A second life. On April 28, 1982, 1 month before Gary Larson published his famous cartoon, Stegosaurus became the official state fossil of Colorado. And behind that fact is a genuinely touching story. The campaign was launched by a class of 4th graders at McElwain Elementary School in Thornton. The children wrote letters to their representatives, collected signatures, and convinced the governor to sign the bill into law. It was in Colorado, near the town of Morrison, that Arthur Lakes had found the first bones 105 years earlier. The kids brought it home. In film, Stegosaurus didn't appear in the original Jurassic Park, contrary to what many people remember. It debuted in The Lost World, Jurassic Park, in 1997, reportedly after a letter from a young fan directly to Steven Spielberg. Stan Winston's team built a full-scale animatronic model nearly 8 meters long and around 5 meters tall. Since then, Stegosaurus has appeared in every film in the franchise, each time looking slightly different because the science underneath it kept moving. But the real story of the 21st century isn't cinema. It's money. On July 17, 2024, at a Sotheby's auction in New York, a Stegosaurus skeleton known as Apex sold. Pre-sale estimate: $4 to $6 million. Final price: $44.6 million. Nearly 8 times the high estimate. An absolute world record for any fossil ever sold at auction. The buyer? Billionaire Ken Griffin, founder of the hedge fund Citadel. The skeleton? 8.2 meters long, roughly the length of a school bus, and 3.3 meters tall. Age? Approximately 161 million years. Found in 2022 on private land in Moffat County, Colorado. Completeness? Roughly 80%. The preserved remains include skin impressions and throat ossicles, tiny bones embedded in the throat skin, rarely found in any fossil specimen. In December 2024, Griffin loaned Apex to the American Museum of Natural History in New York for 4 years. The skeleton went on display in the Richard Gilder Hall. A serious scientific program launched alongside it. A 3-year postdoctoral fellowship funded by Griffin, formal species identification, the first ever growth curve for Stegosaurus, permanent removal of a femur section for laboratory analysis, and a complete 3D model for open scientific use. The most expensive dinosaur in history may become one of the most scientifically valuable. There is, however, a tension this story that troubles the paleontological community and deserves to be named directly. Major scientific journals don't accept research based on fossils in private ownership, because science requires permanent, open access to specimens. Any researcher must be able to physically examine and independently verify the material. Griffin made Apex accessible, and that matters. But what happens in 4 years? And what about the dozens of other significant fossils bought by collectors with no equivalent sense of responsibility? Every skeleton that enters private ownership is potentially lost data. Every auction is a financial incentive for illegal excavation. Then something even stranger happened. In December 2024, the investment platform Rally conducted an IPO of a dinosaur. Yes, an initial public offering. A Stegosaurus skeleton from the Bone Cabin Quarry in Wyoming, approximately 160 million years old and 7 meters long, was divided into 200,000 shares at $68.75 each. Market capitalization at offering, nearly $14 million. All 200,000 shares sold within minutes of trading opening on December 20th. Each shareholder holds a fractional stake in the skeleton, with the expectation that in roughly 1.5 to 2 years it will be sold and profits distributed. A dinosaur as an asset class. Stegosaurus on an exchange. 150 million years ago, this animal grazed among ferns, swung its tail, and may have flushed its plates red for a mate. Today, its skeleton is a tradable security. Between those two facts lies an abyss of time in which all of human civilization fits. Every war, every empire, every discovery, every mistake. Stegosaurus outlasted all of it, first in flesh, then in stone, now in shares. Meanwhile, science keeps moving. In 2022, Bashanosaurus primitivus was described from China, one of the oldest Asian stegosaurs yet found. In 2024, the first well-preserved skull of Dinosaurus, a large European stegosaur described as long ago as 1875 by Richard Owen, was finally documented. For 149 years, paleontologists had known Dinosaurus from body bones only. In 2024, they saw its face for the first time. What about color? Since 2010, when preserved melanosomes, the organelles that carry pigment, were identified in the feathered dinosaur Sinosauropteryx, science has developed tools for reconstructing the coloration of some extinct animals. In December 2025, a paper described the first evidence of coloration in a sauropod from the Morrison Formation, the same ecosystem where Stegosaurus lived. Melanosomes in preserved scales pointing to a spotted or mottled pattern in reddish-brown and black tones. For Stegosaurus itself, no melanosomes have been found. Its known skin impressions don't preserve pigment-bearing structures. Every color reconstruction in films, books, and museum displays is artistic interpretation, not science. But one thing can be said with reasonable confidence. A large herbivore with prominent display structures almost certainly had species-specific coloration. Giraffes have it. Iguanas have it. Mandrills have it. What Stegosaurus actually looked like, we may never know. Epilogue. A century and a half, and one question. Let's go back to where we started. A world without flowers. Without the Rocky Mountains, the Alps, or the Himalayas. A semi-arid savanna with fern ground cover and conifer forests along the riverbanks. Through that alien landscape walked an animal 6.5 meters long, with a 70-gram brain and 2 rows of bony plates rising from its back. It couldn't chew, only shear and swallow. It couldn't outrun its predators, only pivot and strike. Its head hung a meter above the ground. Its tail, with 4 bone spikes at the tip, hit hard enough to punch through the vertebrae of an Allosaurus. We learned of its existence in 1877 and immediately got almost everything wrong. The name, a mistake. The posture, a mistake. The plates, a mistake. The second brain, a mistake. Over 150 years, paleontology has corrected nearly every misconception Marsh introduced. The tail spikes finally got a name, from a newspaper cartoon. Sophie let us see Stegosaurus in 3 dimensions for the first time. We learned that young individuals displayed and old ones fought, that its relatives lived on every continent, that one of them evolved a bone Aztec war club on the end of its tail. In 2024, a Stegosaurus skeleton sold for $44.5 million. In 2025, one was floated on a stock exchange. And we still don't know what the plates were for. 150 years, 4 serious hypotheses, no final answer. Maybe that's precisely where this animal's power lies. Stegosaurus is a reminder that the world was unimaginably different, that what we see around us is not a permanent condition, just a moment, that time is not a straight line, but an abyss, that a creature with a 70-gram brain can survive for 10 million years, that we are chronologically closer to T-Rex than T-Rex was to Stegosaurus, and that science is not a collection of final answers. It's an honest, ongoing attempt to ask better questions. Stegosaurus has been posing its question for 150 million years. We've been trying to answer it for a century and a half. The work continues.